The world is made up of matter. More than 2,000 years ago, a Greek philosopher named Democritus suggested that matter was made up of tiny particles. He postulated the particle theory of matter. The first postulate, or point, in the particle theory of matter is that all matter is made up of tiny particles. For example, one drop of water has 30 kajillion particles. Principle number 2. Each pure substance has its own kind of particle, which is different from the particles of other pure substances. For example, water particles are different than ethanol particles. Principle number 3. The particles of matter attract each other. When the particles are far apart, the force of attraction is very small. When the particles are close together, the force of attraction becomes stronger. But these particles can't get too close. They repel each other when they become too close with a really strong force. Point number 4. Particles are always moving. The particles of solids, though they are close together, are continuously moving. They're vibrating back and forth in fixed positions. The particles in liquids are a little bit farther apart, and they can move past one another and are moving much more quickly than those of solids. The particles of gases, for example, imagine the particles of air inside a balloon. They're moving really fast, and they're moving at distances that are very far apart from one another. Principle number 5 of the particle theory of matter states that particles at a higher temperature move faster on average than particles at a lower temperature. So the greater the temperature, the greater the speed of the particles. Let's go over a few definitions. Let's define matter. Matter is anything that has mass and volume. Mass is the measure of the quantity of matter in an object. And volume is a measure of the space that an object occupies. Matter can exist in 3 different states: solids, liquids, or gases. 3 states of matter can be transformed into the other with the addition or removal of heat. Let's take a look at Figure 1, the states of matter. In Figure 1, we can see the 3 states of matter: solids, liquids, and gases. We have a diagram of the particles of solids showing they're close together, a diagram of the liquid particles showing that they're farther apart, and a diagram of the gaseous particles that show that they are the farthest apart. All matter around us can be classified. We can classify matter into 2 categories. Category number 1 is pure substances, and category number 2 is mixtures. We're going to take a look at pure substances. Pure substance is matter that contains only one kind of particle and has a unique set of properties. Each pure substance has its own kind of particle, which is different from the particles of other pure substances. Pure substances can be broken up into elements and compounds. If something is defined as a pure substance, then it must either be an element or a compound. An element is a pure substance that cannot be broken down into simpler parts by chemical methods. Examples of pure substances include oxygen, gold, helium. I'm listing off a few different elements that exist in the universe, but really there are only a small number of elements that can be classified as elements in the universe. A summary of all of the elements in the universe can be found on what we call a periodic table of elements. A periodic table of elements contains all of the elements in the universe that we know of, whether we have discovered them and seen them, or whether we have predicted their existence. If you take a look at the periodic table of elements, you'll see some elements that are familiar to you. For example, oxygen, chlorine, helium. We'll come back to this periodic table many times throughout this unit. For now, what I want you to realize is that if something is classified as an element, then it must be on the periodic table of elements. If a pure substance is not an element, then it must be a compound. A compound is defined as a pure substance made up of two or more different elements that are chemically combined. Examples of compounds may be familiar to you, such as carbon dioxide, or water. If a substance is not a pure substance, then it must be a mixture. A mixture is matter that contains more than one kind of particle. For example, we have pure substance A and pure substance B. If we mix them together, we would make a mixture of A and B. Mixtures can be classified into two categories. The first is a solution. A solution is the different substances that make up the mixture and are not distinctly visible. Basically, if you take a substance and put it in a liquid and it dissolves, we create a solution. Solutions are also known as homogeneous mixtures. This type of mixture is uniform throughout. If you look at it, it appears as if it's made up of only one phase. Solutions always contain two components. Number one, the solute. The solute is the substance that dissolves. The second component, number two, is the solvent. The solvent is the substance which the solute dissolves in. Examples of solutions: Kool-Aid, salt water, coffee, alloys of metal like stainless steel, Gatorade. These are all examples of solutions. They contain solutes that were dissolved inside solvents. For most of these examples, the solvent was water. I mentioned alloys. Alloys are solutions of two or more metals. We use alloys in jewelry, making motor vehicles, sport equipment, and household items. If a mixture is not a solution, we say that a mixture is a mechanical mixture. Mechanical mixtures are mixtures in which the different substances that make up the mixture are distinctly visible. You can see them. We call them heterogeneous mixtures. They are not uniform. When we look at them, they contain more than one phase. The particles don't mix well together. Examples of mechanical mixtures include oil and vinegar, a granola bar in which you look at and you can see the various components inside, a pizza which is comprised of many things, and these different things are visible to you, such as the crust, the cheese, the pepperoni. In this diagram, we have labeled various elements and various compounds. Let's go through them. Oxygen is an element that's in the air. Titanium oxide is a compound that is found inside sunscreen. Aluminum is an element that is used to make a drinking can. Gold is an element used in jewelry. Sodium chloride is a common compound, and it's known as table salt. Acetic acid is commonly known as vinegar and is also a compound. Silicone is an element used to make electronic devices. And water is a compound, and it's essential for life. Scientists now call the particles of the particle theory atoms. An atom is the smallest unit of an element. Each element is made up of only one kind of atom. Atoms join together in combinations. When two or more atoms join together, a molecule is formed. Let's take a look at some examples. Here we have a hydrogen atom. All hydrogen atoms look the same. Beside it, we have an oxygen atom. All oxygen atoms look the same. I'm coloring the oxygen atom in red. Both hydrogen and oxygen are elements and can be found on the periodic table. Water is a compound, and water is made up of water molecules. A water molecule consists of 3 different atoms. Let's see if you can figure out what atoms make up water. You can tell by the way I'm coloring it in that a water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. Methane is a compound. Methane is the compound that is commonly known as natural gas. A methane molecule, one particle of methane, is made up of 4 different atoms. A carbon atom, this is the large central atom, and 4 hydrogen atoms. Next, I have hydrogen peroxide. Hydrogen peroxide is a compound. You may have a bottle of hydrogen peroxide in your first aid cabinet at home. Hydrogen peroxide is made up of 4 atoms. One molecule of hydrogen peroxide contains 4 atoms. Let's see if you can guess which atoms it's made up of based on the colors in which I'm coloring in the atoms in one molecule of hydrogen peroxide. That's right. There are 2 carbon atoms and 2 hydrogen atoms. As I mentioned before, all of the elements known are listed on the periodic table. Every element on Earth is organized on this chart called the periodic table. These are all of the elements in the universe that are known to man. As of 2016, there are 118 known elements in the universe. These elements can join together to form compounds. We use chemical symbols to represent the elements. A chemical symbol is always made up of 1 or 2 letters. You can see all the different symbols on the periodic table, and if you look closely, they're made up of either 1 or 2 letters. Take a look at these symbols and see if you can see a pattern. The first letter of each of these symbols is always a capital. If there is a second letter, it's always in lowercase. The symbols are often derived from their non-English names. Let's look at a few of them. The symbol for hydrogen is capital H. This is the first element on the periodic table. And you can see it's labeled number 1. Calcium has the chemical symbol capital C, small a. Helium has the symbol capital H, small e. Silver has the chemical symbol Ag. Lithium, capital L, small I. And gold, capital A, small u. What I want you to do is to use the periodic table to list the names and symbols for the first 20 elements on the periodic table. We already mentioned that the first element on the periodic table is hydrogen, and it has the symbol capital H. Hydrogen has the atomic number 1. Let's look at the second element on the periodic table, the element that has atomic number 2. See if we can find it. The elements on the periodic table are numbered from left to right and up and down. So if hydrogen is number 1, you guessed it, helium is number 2. Lithium is number 3. Beryllium is number 4. I want you to use the table to list the first 20 elements and their correct symbols. Chemical formulas exist in science, and they're used to represent compounds. A chemical formula represents 2 or more elements which are chemically combined to form a molecule or a compound. They tell us the different elements that are present, and they also tell us how many of each. For example, we have the chemical formula H2O. This is the chemical formula for water. It tells us that there are two different elements, the H and the O. H, from the periodic table, we know is hydrogen. And if we look for the symbol O on the periodic table, we know it's oxygen. Not only does it tell us which elements are present in one molecule of the compound, it also tells us how many of each there are present. There's a little number 2 beside the H. That means that there are 2 atoms of hydrogen in one molecule of water. Now there's no number written beside the oxygen. If no number is written, we assume that there are 1 atom of oxygen per molecule of water. If you remember the diagram we drew up above, a water molecule can be represented like this. 1 main oxygen atom and 2 smaller hydrogen atoms. How do you count the atoms in a compound? The symbol of an element represents 1 atom of that element. For example, the symbol Na stands for sodium. A subscript is a number written in the lower right-hand corner beside the symbol of an element. If there is more than 1 atom of the element, then a subscript is used to indicate the number of atoms. For example, H2 has the subscript 2. That means 2 hydrogen atoms. A subscript outside of a bracket multiplies all of the elements inside the bracket. Let's take a look at this compound called magnesium phosphate. Magnesium phosphate contains 3 elements: magnesium, phosphorus, and oxygen. There's a subscript 3 beside the magnesium. That tells us that there are 3 magnesium atoms in one molecule of magnesium phosphate. Now you'll notice that phosphorus and oxygen are found inside brackets. If they are found inside brackets, then you'll need to multiply the number of phosphorus atoms by the number outside, which is 2, and the number of oxygen atoms by the number outside. So, phosphorus doesn't have a subscript. So that means there is 1 phosphorus atom inside the bracket, and we're going to multiply it by the 2, which is outside the bracket. So we know that there are 2 phosphorus atoms in one molecule of magnesium phosphate. If we look at oxygen, it has a subscript of 4 inside the brackets. We are going to multiply that 4 by the number 2 outside the bracket. And 4 times 2 is 8. So there are 8 oxygen atoms in one molecule of magnesium phosphate. We can add up the total number of atoms in one molecule of magnesium phosphate. 3 plus 2 plus 8 is 13 atoms. In one molecule of magnesium phosphate. Let's take a look at a few examples. H2O. H2O contains 2 hydrogen and 1 oxygen. Next we have copper sulfate. Copper sulfate contains 1 copper, 1 sulfur, and 4 oxygen. Next we have lead nitrate. Lead nitrate. Let me just make a small correction here. Make sure we have the correct elements. You may want to do the same on yours. Contains 1 lead atom. Next, inside the bracket we have nitrogen. And there's no subscript beside the nitrogen, so we know that inside the bracket there is 1 nitrogen. We're going to multiply that by 2. So we know that 1 times 2 is 2 nitrogen atoms. Finally, we have oxygen. And inside the bracket, there are 3 oxygen atoms. We're going to multiply the number inside by the number outside. And 3 times 2 is 6. Chemical formulas also represent something we call diatomic elements. Diatomic contains the root words di, which means 2, and atomic, which means atoms. Diatomic elements are elements that are rarely found by themselves in nature. For example, oxygen is never found on its own in nature. It's always found paired with another oxygen. So we write the diatomic element formula for oxygen as O2. O2 is in the air we breathe. Hydrogen is another element that is found in diatomic form. Similarly, chlorine is also found in a diatomic form. The complete list of diatomic elements can be remembered by saying Hofbrinkel. Hofbrinkel contains all of the elements that are diatomic in nature: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Hofbrinkel. There are many ways to describe matter. We describe the physical properties of matter as characteristics of a substance that can be observed and measured without changing the identity of a substance. Physical properties can be qualitative in nature. Qualitative means that you can observe these properties without any detailed measurements. Properties that describe the characteristics of a substance using your 5 senses: smell, sound, touch, and taste. The first qualitative physical property is color. This is the color emitted by a substance. The second is texture, how matter feels. For example, sandpaper is very coarse and can be used to create a smooth texture on wood. Coarse and smooth are physical properties. Odor. how matter smells. Luster, how shiny an object is. For example, gold is shiny and has high luster, while concrete is dull and has low luster. Clarity, how well you can see through matter. If you can see completely through matter, we say it's transparent. For example, clear glass. If you can partially see through something, we say it's translucent. For example, frosted glass. And if you cannot see through something, then we say it's opaque. The final qualitative physical property is taste, how matter tastes. We describe the taste of matter with scientific terms, such as sour, salty, sweet, and bitter. Next we have the state of matter. The state of matter can be solid, liquid, or gas. Ductility is the ability of a solid to be stretched or pulled into wires. For example, copper is a metal that can be pulled into wires. Copper is ductile. Malleability is the ability of a solid to be hammered or rolled into sheets. For example, aluminum foil is an example of a malleable metal that can be hammered into sheets. Viscosity is the resistance of a fluid to flow. Water flows quickly, and we say it has low viscosity. Honey flows slowly, and we say it has high viscosity. We mentioned the changes of state. The change of state of a pure substance from solid to liquid is called melting. The change of state from a solid to a gas is called sublimation. The change of state from liquid to gas is called evaporation. Liquid to solid, freezing, or solidification. Gas to liquid is called condensation. Gas to solid is called deposition. This diagram summarizes the different changes of state that occur. Our second group of physical properties are called quantitative physical properties. Quantitative physical properties contain the root word quantity. These are properties that are based on measurements or counting and can be assigned a particular numerical value. For example, the first quantitative physical property is melting point and boiling point. These are temperatures. For example, the melting point of water is 0 degrees Celsius. The melting point of ethanol is minus 114 degrees Celsius. The boiling point of water is 100 degrees Celsius, and the boiling point of ethanol is 78 degrees Celsius. The second quantitative physical property is solubility. Solubility is the ability of a substance to dissolve into another substance. The opposite of soluble is insoluble. A substance that is insoluble has low solubility. Next, we have hardness. Certain substances are harder than others. For example, diamond is the hardest natural material known to man. and has a hardness value of 10. The hardness scale is measured from 1 to 10. Conductivity is the ability of a substance to conduct electricity or heat. Copper, for example, is a good conductor of electricity. And that's why we use it to make electrical wires. Styrofoam and glass are not good conductors. If something does not conduct heat or electricity, we call it an insulator. Density, and we put a little asterisk beside density. It's the amount of mass in a given volume of a substance. The density of water is 1 gram per centimeter cubed, and the density of olive oil is 0.9 grams per centimeter cubed. Water is more dense than olive oil. That means that olive oil would float on the surface of water. The asterisk represents characteristic properties. We gave density an asterisk, and I also want to give melting and boiling point an asterisk. So these characteristic properties mean that these properties belong to one substance and one substance only. For example, water boils at 100 degrees Celsius. Only water boils at that temperature. The density of olive oil is 0.9 grams per centimeter cubed. The density of water is 1 gram per centimeter cubed. Only water has a density of 1 gram per centimeter cubed. If you know the characteristic property, then you can identify the identity of the substance. There are chemical properties of matter as well. A chemical property is described as the ability of a substance to change or react with another substance to form one or more new substances. Chemical properties include how a substance interacts with other substances, such as acids, or how it reacts to heat or to light. Chemistry based on reaction between substances to synthesize new chemicals with different properties. Chemical properties can be observed only when a chemical reaction or change takes place. Some of the chemical reactions that elements and compounds undergo are as follows. Number 1, reactivity with water. This is the first chemical property. Alkali metals, for example, lithium, sodium, potassium, react with water to produce bubbles of hydrogen gas. The second chemical property is reactivity with oxygen. Iron, for example, reacts with oxygen to produce iron oxide. This is commonly known as rust. It is scientifically a chemical reaction called oxidation. The third chemical property is reactivity with acids. Sodium bicarbonate, also known as baking soda, is a compound that reacts with acids like acetic acid and vinegar to create carbon dioxide gas. This is a common experiment that is often called the volcano experiment. The last chemical property is combustibility, and this is the ability of a substance to burn in oxygen. Candles and matches are combustible and will burn in the presence of oxygen. Sometimes matter can change. matter can go through physical and chemical changes. A physical change is a change in a substance that does not involve the formation of a new substance. So the substance involved remains the same substance, even though it may change its form, it may change state, or it may even dissolve. The particles that make up the substance remain the same particles throughout the change. Examples of physical changes in matter can include a change in form. For example, ripping paper, or breaking glass, or crushing a stone. In each of these changes of form, the particles still remain the same. The second type of physical change can be a change of state. For example, melting gold or evaporating water. These physical changes are reversible. You can condense water. You can cause melted gold to form a solid again by cooling it. The third physical change is called dissolving. Dissolving is when a solute dissolves inside a solvent. Examples include dissolving sugar in water or dissolving carbon dioxide in soda water. Now, there are different types of changes that are called chemical changes. A chemical change in matter is one in which one or more new substances are formed. The original substance has been changed into a brand new different substance that has different properties. The particles in the new substance are different from the particles in the original substance. If a chemical change occurs, there are 5 clues that could indicate that in fact a chemical change has occurred. Clue number 1, a new color appears. Clue number 2, heat or light is given off. Clue number 3, bubbles of gas are formed without adding heat. Number 4, a solid material called a precipitate forms in a liquid. And number 5, the change is difficult to reverse. Note, just because a clue is seen, it doesn't mean that a chemical change has occurred. It just suggests that there may have been a chemical change. A precipitate is a solid that is formed in a chemical reaction and occurs in an aqueous solution. Aqueous means a solution that contains water. Here are some examples of physical changes. For example, burning a log, rusting a nail, rotting fruit. And below we have examples of chemical changes. For example, iron rusting, wood burning, chemical digestion inside your stomach, the cooking of an egg, the baking of a cake. I want you to work on your homework questions for this section.